Bismillahirrahmanirrahim. Assalamu alaikum and good morning to my students. So today is the physics day, and you know that we are doing this book. And this book, we are at chapter number one, and the chapter number one is about measurement, making measurements. In fact, to be very precise, and in measurements, we have already done a length and a volume and density. We have studied three things so far: uh, length, volume, and density. Yes, length, volume, and density. In length, there are also three things. Everything is length, if in broader terms. It is also breadth. Breadth is also length. Height is also length. Okay, height is also length. And in volume, we have learned about area multiplied by length or height, or and in density we have learned d is equal to m upon v. Okay, now so far we have learned these things, but today what we are doing is measuring time. Now, for example, we are conducting an experiment. Yes, from experiment, I recall that if the time allows, I'll be doing the practical of density today. I'll be doing practical of the density in today in my kitchen. Okay, because I'll use the kitchen skills to conduct this practical. Okay, if the time allows. Measuring time. For example, there's an athlete when he sprints, the time is noted by his coach or her coach, how many time he takes to complete the 100 meter. The lesser the time he takes, that means he is faster, he is more faster. The lesser the time he takes, then he is more faster. And even the fraction of the second is counted. The fraction of the second is counted. But but what we do when we do have the clocks, clocks which are hanging on our which are hanging on the walls of our rooms, and on the platforms, on our wrists, that is wristwatch, or the clocks, or the stopwatch with hands in it. There are how many hands? Usually there are three hands in a clock. There are three hands in the clock, like this. This is a clock, and there are three hands. One, two, three hands, or arrows, or pointers. You can say whatsoever. But these are oftenly called. These are called hands. The number one is the hand of seconds. It is the hand of seconds. And number two is hand of minutes. And number three is hand of hours. And this clock is divided into 12 equal parts. As you know, you have seen all over the world, or in your houses, on your wrist, that it is divided into 12 equal parts. Okay, and now these 12 equal parts are 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And in this, from 12 to 1, there are five parts again. That means when the second, this is a hand of seconds. When this struck like this to 12 and a 1 division, From 12, it travels a distance of 1 division. It will travel 1 second only. It will travel 1 second only. That means that we have only the least count which we can measure on this wall, on this clock, on this stopwatch is 1 second. This is the 1 second which we can least count on this watch, and these watches are called analog watches. Analog analog watches. These are called analog watches. But there is a very disadvantage. For example, when a sprinter sprints for 100 meters, if one sprinter takes 10 seconds to reach from 0 point to 100-meter point, 100-meter point, he takes 10 seconds. Okay, and the other sprinter takes less than 10 seconds. He takes less than 10 seconds. Less than 10 seconds. We cannot measure the two. We cannot measure the two. How many less? How many less than 10 seconds? Either it is 9 seconds or 10 seconds. We don't have any instrument. We don't have anything which could have measured from 9 seconds to 10 seconds in this analog clock, okay, or analog stopwatch. But today we do have a digital clocks, and you know the world record for a sprint of 100 meters is 9.58 seconds. Now you see that the second is further divided into 100 parts. 1 second. This 1 second has been divided. This 1 second. 1 second is divided into 100 equal parts. 100 equal parts. So this 100 equal parts will tell you how much less than 10 seconds. How much less than 10 seconds. So which we could have not measured on this clock, we will measure it on the digital clock. The digital clock 958. How it is made, I'll be telling you in future when we study electronics. We'll be studying electronics. 9.58. Okay. Now these digital clocks, though these are very cheaper, they are in the from these clocks. These are very cheaper from these clocks, but are very precise. These clocks are very much expensive, especially when it is made in Switzerland. Switzerland has some brands of making these clocks or watches. And they also manufacture for these on special orders. And there are some clocks or watches which are made only once or twice or thrice. Okay, you might have heard that there are only 3 watches which are made by Switzerland from a company of Switzerland, and these are very much costly. Even then, they cannot beat the accuracy. They cannot beat the accuracy of digital clocks. Okay. Now these are the digital and now if you want to, what is the importance of our of measuring time in our daily life? What is the importance of it? I have given you example of the sprinter, and you might be doing some practical. You might be doing some practical in your lab, in which chemical action has taken place, in which a chemical action has taken place. Okay, and you have to stop this chemical action after, let us say, 10.5 seconds, 5 3 seconds maybe, to be more precise, 5 3 seconds. You have to stop this. What will you do? You will not use this clock. You will use the digital clock or digital stopwatch to uh, stop this, or note the reading of that chemical action at 10.53 seconds. You have to log that. Okay. On the railway stations, you might have seen big clocks like this. Big clocks like this, uh, very antique and very big watches you might have seen on the railway stations platforms, and the time can be seen from very far. If you are very far from the this watch, you can even see, or you can even read the time over here. Okay. Now what about if I want to measure the short intervals of time? I want to measure the short intervals of time. Let us consider one experiment. Let us consider one experiment today. Okay. Now there is a lab, physics lab. You are in physics lab, and it is a table. Okay. This is the corner of the table, and there is a stand. There is a stand. Okay. And on the stand there is a rod, and on the rod there is a clamp. There is a clamp which can be tightened, and in the clamp a spring has been dropped, and 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 at one end of the string a bob, plumb bob. This is called a plumb bob. Plumb bob. Plumb bob. So this is plumb bob. This is made out of steel. Okay. Now this is a string. Okay. Now this is a string which is hanging on the stand, and the weight acted by this ball is like this, and it is of course it is the gravity of the earth is pulling it down. Gravity of the earth is pulling it down. Okay. Now what happens next? If I give it a gentle push, it will start oscillating from one point, from its center point to here. Okay. It will start oscillating. It will leave its initial position, and it will go to the higher altitude. But it will go to the higher altitude if I take this as a point. If I take this as a point, you see that this distance is less, this is greater. Maybe this is 10 centimeter, and this may be 12 or 13 or 14 centimeters. Okay. Because why is this? Because this bob is attached and fixed at one place. It is attached and fixed at one place. It cannot go beyond this point. Okay. So it will move from here. Now this is working as a center. This is working as a center, and this is the radius of this bob. So the motion will be circular. The motion will be circular. Now when it will reach its highest point, the momentum will come here, the zero, or the kinetic energy will be zero. Okay. When the kinetic energy will be zero, so it will stop at this point for fraction of a second. Okay. And it will start traveling backwards. It has exerted so much kinetic energy that it will cross its initial point at it, and it will come over here. It will come over here, and again the same phenomena will be done, and it will go, and it will keep on oscillating to and fro, to and fro. It will be oscillating to and fro. Let me explain it to you practically. I have a book for you, and this is a bricklayer. This is a bricklayer book. Bricklayer always keep these book with them, and carpenters also do. So this is a book. Let me do it a little shorter. Let me do it a little shorter. Now, you, my dear students, you see that this is the same figure over here. Okay. Now, if now in initial it is at rest, and if I give it a gentle push, you see it has started oscillating. It has started oscillating, and you see that this distance is lesser and this distance is greater. This distance is greater, but this is the same distance. This distance will remain the same because this is fixed at one point and it is moving at the other point like a compass. Okay. Now this thing, this is a very important exercise. This is a very important practical. And what is this? This is oscillation from it is traveling from here to here and back here to here. This is called the oscillation. And one complete oscillation, it has started from point zero, center point, and went up there, came back to its center position. By virtue of the kinetic energy, it is again gone up to the other side, and now this complete is one oscillation, and this is called one period. What is this called? This is called one period. Okay. Now, measuring this is one period. If we just start our stopwatch, we measure this from here to here and here to here. We'll measure this for one period. It will not be very accurate. It will not be very accurate. Then what will we do? We will be counting it for 20 or more periods. 20 or more periods. We will be counting it for 20 periods or 20 oscillations. Okay. And then we'll note the time, and we'll do our practical as we are told to do. Yes, there is a practical over here or about the this oscillating bob, and it is a student was investigating how the period of pendulum varied with the length of the string. And yes, there is one important thing, very much important thing. I just skipped from mine. You might have seen these clocks as well. You might have seen these clocks as well. Okay. These are holes for to wind the key, and like this it would have been like this, and there's a pendulum hanging over here. There's a pendulum hanging under this pendulum is made out of brass. Usually this is the pendulum used uh, in these watches, pendulum watches. These are called pendulum watches. This is instinct now, and maybe some antique collector have these. Okay, now this pendulum was made out of brass, but this pendulum was equipped with some threads underneath, and a nut. A very sophisticated or precise nut was also equipped with this. What happened to it? By this nut, we can change the position of this brass bow. It can either go upward, maybe 2 millimeters, let us say 2 millimeters, or it can come 2 millimeters down. or it can come 2 millimeter down by virtue of this nut. By virtue of this nut, what happened? The interesting thing is what happened, that by the oscillation of this pendulum, when the length of the string, when the length of this pendulum is increased or decreased, when the length of this length is increased or decreased, it will affect its oscillation. It will affect this oscillation. And when the oscillations are affected, the time, the speed of time, you know what is the speed of time? For example, this watch is running in actual, today I set it at 1 o'clock. Okay, today I just set this clock at 1 o'clock, and the next 1 o'clock, this on 1 o'clock on the digital clock. I have checked this on the digital clock. Today is 13 January maybe, or 14 January. This is 1 o'clock over here and 1 o'clock over here on 14. What happened? 14 January. The It is 12:59. It is 12:59, whereas this clock has struck again 1 o'clock. That means this clock is running ahead of time. This clock is running ahead of time because the speed of time for 24 hours is 1 minute more. 1 minute more than the actual time. 1 minute more than the actual time. So we can adjust this. We can either lower it down or we raise it up to adjust this time to this time. That means the speed of time can be controlled by adjusting this knob or the nut. Okay, now you would have understand that this length is of prime importance. This length is of prime importance in this pendulum business. Okay, now what he did, a student was investigating how period of a pendulum varied with the length of string and obtained the result in table 1.4. So this is table 1.4, which is on page number 11. Length of string 0, 0.2, 0.4, 0.6, 0.8, 1, 1.2 and 1.4 per meter. Okay. What happened? What happened? The longer the string goes, the longer the time is taken. The longer the string goes, the longer the time is taken. For example, this is 0.2 meter. 0.2 meter means this much, maybe this much. Okay, this much. Okay, 0.2 meters, and you see what is happening. It is not oscillating very much. It is not oscillating very much. Okay, and after it is 0.4 meters, it has come 0.4 meters. Now this is 0.4 meters. If I just 0.4 meters, 1 2 3, okay, this is okay, 0.4 meters come over here, this will be 0.4 meters. Now you see that the time taken for 20 oscillations, I told you we usually take 20 oscillations. So the time taken for 20 oscillations will be 18.1 second. 18.1 second. So we can calculate the time taken by one oscillation. And similarly by 6.1 and 1.4. And when it came to 1.4, I don't have 1.4 meter string. I have only about 1 meter string. Okay. Now 1 meter string is, if I oscillate it for 20, it will take 44 minutes. 20 oscillations will take 44 minutes, 44 seconds. Okay, 20 oscillation will take 44 seconds. Now that means the longer is the length of the string, the longer the time period has been taken. The longer the time the string is, the longer the time period is there. So there are questions. Why did the student record the time for 20 oscillation? I already told you, because when we uh, put on our stopwatch, maybe I am a little late or I am a little early to on the clock, put on the clock. So with one oscillation I cannot take the accurate reading, I cannot take the accurate reading. So 20 oscillations are taken and counted to get the average, and 1 by 20 will be your result. Make a copy of table for each length of pendulum, calculate the time for each oscillation. So these are the practical questions, so we need not to do it. Okay, this using a pendulum clock was uh, made in 1656 by a Dutch scientist. Okay, so what is our next? Okay, we have finished it. Okay, we have finished it. The time measuring time was just this much, and yes. Now question number 8 on question page number 11. Now suppose I am making this video. I'm making this video. So high speed video, in sports, even in cricket, maybe in cricket, you see that the slow motion is always replayed to you for catches, for stump outs, for run outs, and all these stuff. Okay, how that may be very advanced technology, but to understand this, to understand this, if I record, if I record any event, maybe run out, usually 24 frames per second. 24 frames per second is the normal speed which we observe, which we watch on TV, on the video. It is 24 frames per second. But the actual, what is actually done, a camera with a special advanced feature is equipped, a camera with a special advanced feature. For example, it is recording at 20 frames per second, 60 frames per second. 60 frames per second. What is the actual speed? 24 frames per second. But the camera is recording at 60. It is constantly recording. It is constantly recording at 60 frames per second. Now, if you drive that, reproduce this result at this speed, it will be very slow, because this has been recorded at faster speed than this. It has been recorded at faster speed than this. So the question is all about this. High speed video can record sporting event at the frame rate of 60. What is the time interval between one frame and the next frame? So it is obvious. So if this is one frame and this is the another frame, so it is 1 by 60 second when the next frame will appear. When the next frame will appear, it is 1 by 60 second. You can calculate it with the help of calculator. I do have one calculator over here. 0.016 seconds. The answer for A is 0.016 seconds. It is the time when this frame has gone and next frame has come. This frame has gone and next frame, or you can say the time taken by one frame is 1 by 60 second. Okay, what is the next? If we can, yes, this is the interesting question. if we can see the 24 frames as continuous motion, what is the factor recorded at 60 frames? We slow down, or so we have recorded this. That means now we have recorded the event at 60 frames per second, and we want to uh, run it at this speed. We want to run it at this speed. So what will be the slowdown factor? Now this is called the slowdown factor. The slowdown factor is slow down factor. You can say it's slow down factor. This is part B of example 8. Okay. Okay. This is slow down factor, which is equal to frame rate of high speed video. Frame rate of high speed video and frame rate of normal speed, which is this one, normal speed video. Now what is this? You can easily manipulate 60 divided by 24. 60 divided by 24. Now this both are have same units, frame per second, frame per second. So it will be cut down, and this will become something like more than 2. Okay, it is 2.5. The ratio is slowdown factor is 2.5. Slowdown factor is 2.5. If we slow it by 2.5, uh, we can watch the same video at the normal speed. So okay. So my dear students, this chapter has been completed, and we can now do examination style questions, and these are about 10 questions. These are 10 questions. Should we do it now or we do it? Okay, I think we should finish these. Question number 1. Use this table to answer the question 1 and 2. Now there is a table given to you. Now these are the numericals, which we call numericals in physics. When the questions are given, these are called numericals. The question at the ends are called numericals. Now numerical, the table is given. Okay, it is all about density now. A table is given with how many? 1, 2, 3. 3 metals. 1, 2, 3 metals. And metals, the name of metals is here. And density. Density is given in grams per centimeter cube. Okay. Density D is equal to grams per centimeter cube. Now gold. Now gold has the density of 19.30. Silver has the density of 10.49. And what is else is there? Lead has the density. Heavier metal is gold and lead. The silver is the less heavier. Okay, you can see that this is the lesser dense material, this is little more dense material, and this is the heaviest material. Okay, that gold is the heaviest of all. Now, what is the question? 3 metal cubes have same volume. Now question is very interesting. Now these, we have taken a cube out of each. Which have the same volume. Gold have same volume AU, silver is AG, and lead is PB. These are uh, their chemical names. Okay, arum, argentum, plumbus. Okay, periodic table. You can see the periodic table. Arum, argentum, and plumbus. Lead, silver, gold. The volume is same. Volume is same. No, volume is same. When volume is same, what is next? But are made of different metal. Each one is lowered into beaker of water. Now each one is lowered into beaker of water. Each one is lower in beaker of water. What will happen? Use the data in the table to decide which one will cause the biggest rise in water. Now, my dear students, what was the Archimedes principle? I told you when we are studying density that the displacement of the water in the beaker, it depends upon the volume of anything. Volume of anything. For example, if this is thrown in water, is dropped in water, the displacement, what displacement will occur? The displacement will be equal to the volume of this pen. And if this is dropped in water, the displacement of this cuboid will be the volume of this cuboid will displace an equal amount. The volume of this cuboid will displace an equal amount of water. Okay. Now there are four options given to you. There are four options given. You followed my point or not? Or do I repeat it? The volume is the water is displaced. The water or the liquid is displaced. You can say it water. Water is displaced equal to the volume, equal to the volume of the thing dropped in it. Water is displaced equal to the volume. For example, the volume is of the cube is 10 cc, 10 centimeters cube, and it was the water was 90 cc in the water was 90 cc. The initial water level was 90 cc, and when you place 10 cc cube in this, it will rise to 10 cc from here. So the total rise, the total after dropping the stone or dropping will be now is 100 cc. That means 100 minus 90 is equal to 10 cc. Understood now? Now, when the volume of each is equal, when the volume of each metal is equal, you just drop one, you just drop the other, you just drop gold, bring it back, note the reading. Okay, note the reading. Drop silver, note the reading. Drop lead, note the reading. You'll see that all readings will be same. All readings will be same because the volume is same. Because in this question, the condition is given that the volume of all the cubes is same. When the volume of all the cube is same, the rise in water will be same. The rise in water will be same. Now, same question 2 again from this table. Three metal cubes have the same mass. Now, the same mass. Water is displaced is equal to volume of the cube. But when I drop a cube whose mass is different at each. Now here the mass will be different, here the mass will be different, here the mass is different. So what will happen to the rise of water? Maybe this is the, yes, this is the question. What will happen to the rise of, and which metal will rise the most? It is use the data and table to decide which one will cause the biggest rise in the water level, which will cause the biggest level rise in the volume of the water. Okay. Now, what is the density? Density is equal to mass per unit volume. mass per unit volume. For example, the mass is same now. The mass is same. M is same for all. M is same for all the cubes. Mass is same of the cubes. When mass is same, that means volume is different. Volume is different for all. Volume is different for all because we have to check the density. For this, it is 19.3 AU. For AG, it is 10.49. For lead, it is 11.34. When mass is same, the volume will have to be different. The volume have to be different because we have taken these two things constant now. This is D is always for gold this for silver will remain this, and for lead will remain this. But on the second condition, we have taken this also constant. Taken this as one constant now. Mass for this is same, this is same, this is same. What will happen? Can anybody tell me what will happen? Let me demonstrate to you by doing one example. Now you see the density is different for all the metals. Now for example gold. Let me take gold first, and the symbol of gold is AU. The density is 19.30. Let the mass be 10 grams. Let the mass be 10 grams for every. Then what will be the volume? The volume will be 10 divided by 19.3 for AU. Okay. Now this will. Now you see mass is same for all. For AG silver, 10 divided by 10.49, and for lead PB is equal to 10 divided by 11.34. Now these are the volumes now. These are the three volumes. Okay. I have taken 10 mass, same mass, same mass, same mass, same mass. But we can take density as it is specified in the table. And these are the standard 19.34, 10. Now what is happening over here? You see 10 divided by 19. 10 divided by 19.3 is equal to 0.51. That volume is now 0.51 grams per centimeter cube. Centimeter cube, grams, not grams. It is 0.51 centimeter cube. 0.1 centimeter. For AG, AG is silver. 10 divided by 10.49. What the result it will give is 0.95, 0.95 centimeter cube. And for plumbus, 10 divided by 11.34, it will give us this 0.88. Again the centimeter cube. Now you see, my dear students, the greatest volume. You can see the greatest. Which is the greatest volume? Now this has the greatest volume. This has the greatest volume, which is silver. Which is silver. Ag, argentum. Silver has the greatest volume. That is almost 1.95 centimeter cube. Now, since the volume is higher of all, it will make the water level rise the most. It will make the water level rise the most, and our answer is yes, is silver. Okay, is B. Answer is B in our case. Okay, silver.